So, we've talked about moving charges and how when they enter a magnetic field, they experience a force, what we call the Lorentz force. And I've tried to explain that this is one of the more important forces of all time, at least in the last couple centuries. And I'll explain that a little later, kind of leave it as a cliffhanger. But most charges are not independent. They're not just floating around. I mean, in some cases they are. When you talk about the old cathode tubes and TVs and monitors, the big wide monitors, not the flat panels, you are talking about electrons that are liberated into some sort of, well, in those cases, vacuums, and then they have a magnetic field in order to guide the beam. But in most cases, charges are found in wires. When we talk about moving charges, we tend to be talking about current in a wire. So what we need to do is we need to come up with another equation to talk about current in a magnetic field and the force that wire will experience because of the current traveling through the magnetic field. Okay? Going back to the equation, QV cross B. We're talking about potential, we're talking about not potential. Talking about velocity. I made that big error. Talking about velocity, talking about magnetic field, and talking about charge. Okay? Well, there's a real simple way of looking at this. So if I were to do a little bit of a unit analysis, I have a coulomb, I have a meter, and a second. Okay? And then I have across the magnetic field, which is in a Tesla. Okay? That's the unit for a magnetic field. It's not a base unit. We can derive units from a Tesla by using this equation, actually, because that ends up equaling force, which is a newton. But Teslas are not base units; they're a derived unit. So I've got a coulomb meter per second. Now we know coulombs per second is a current. Okay, so if I have a current multiplied by a distance crossed with a magnetic field, I'm going to get a force. So what I have right now is I have the makings of a really, really simple way of looking at magnetic fields in a wire. So the current multiplied by a distance. So if you look at it, I have a long piece of wire. And that long piece of wire is in a uniform magnetic field. So I have this magnetic field in that long piece of wire. Okay? And then we have a current traveling through that piece of wire. Okay? Now where's the force? Well, the force is across the entire length of wire, because there are all these charges in that wire that are moving in a general direction. I mean, they're relatively random. I mean, they've got random motion going on, but the net motion of all those charges is in that direction. Okay? So we've got moving charges, we've got a magnetic field. So where is the force? It's over the entire length of that wire. So when we talk about current multiplying by a length, we mean the length of that wire. Okay? Now you can think of it as a position vector, or as position or displacement. So we can consider that to be a vector. Okay? But most of the time we consider it to be a vector associated with the current. But current's not a vector, but it does seem to have a direction. Okay? So I do have current in this direction. And I cross that with B. Okay? So I cross with B, force. Moving in this direction. The wire bends that way. Okay? If it's allowed the freedom to move, it will move that way. And that would be the bell. I'm going to let it finish. Okay? So the wire is pushed in that direction. Okay? IL cross B. IL, the current and the length of wire, cross with B. The magnetic field is going in this direction. I've got my push. So the equation we're looking at is IL B. That's the force that I'm experiencing. So that's force experienced on a piece of wire that has a current moving through it. Cool?